Greetings everyone and welcome to today's video on linear mixed effects regression and how to model linear mixed effects models in R. First of all, before starting writing a code, for those who are new to mixed effects models, what are they? What are they used for? How are they different from simple fixed effects models? And what are fixed and random effects and how they're different? So we will start by covering a few of these definitions. For a relatively detailed understanding, I would encourage you all to read the text, but I will summarize in brief and only highlight the important points. When you want to model longitudinal data, or in a broader sense, clustered data, you can go either of two ways when your dependent variable is continuous. You can either use a repeated measures ANOVA, also known as RM ANOVA, if you have longitudinal data, for, as the name suggests, repeated measures, or if you want to build a complex model where you want to adjust potentially for many different variables or factors, such as, say, demographic factors, any other physiologic factors, or any other factor which you think might confound or influence the results. You cannot do that in RM ANOVA. It's just a simple analysis of variance technique. But in regression models, you are able to do that. So in essence, when you have clustered data, you should look into using a linear mixed effects model when you have a continuous dependent variable. Now, what are fixed and random effects? Very simply put, random effects are those variables or effects which are the clustering effects. So suppose you are collecting data about certain trees in the entire world, a certain genus, a certain species of trees throughout the entire world, and you want to find out certain characteristics. Now, there are certain characteristics in say country A, country B, country C, country D, and so on, which are very unique. It can be anything: the soil, the water, the temperature, the amount of light it receives, and so many other factors which you cannot possibly account for, or you cannot possibly fathom or adjust for in the model. And because of these unique factors for each individual cluster, these data from a single cluster are correlated with each other. In one single cluster, data are correlated. In cluster B, data are correlated. In cluster C, data are correlated, so on and so forth. So how do you explain this in a model, or how do you account for this in a model? You define them as something known as random effects, and this is exactly what we will be doing. So you might say, okay, so clustered effect. So how does longitudinal data come into the picture? Now here's where it gets interesting. Each individual in longitudinal data can be thought of as a single cluster. For example, if you get data from, say, 10 patients over 1 hour, over each 5 for every 5 seconds, say you want to take the systolic blood pressure every 5 seconds for 10 minutes for 10 patients. Now, won't there be physiological factors or any other factors which are unique to each individual? Of course. So how do you account for this? You consider each patient as a cluster, you consider each data as a cluster. So here is when you will adjust for the subject as a random effect. Here is when you will account for this effect, this variable, as a random effect. Now, without further ado, let us start by modeling mixed effects model. Now, the first thing, as we always do is to load libraries which are going to use the LMER, linear mixed effects regression test. Alternatively, the LME4 package, both can be used to model mixed effects models. There are many other packages. These are the most commonly used to model linear mixed effects. So when your dependent variable is continuous. So these models are also called hierarchical models because there is a certain hierarchy to the data structure which will become apparent when once we explore the data even further. So for this tutorial, we'll be using a data on theophylline, which is a drug. Data on theophylline concentrations in patients. So first of all, let's load the data set theophylline, and this is included in the datasets base R package, so you can directly load it. And these this explains what the dataset is all about. So subject is of course data pertaining to which subject, so that it 1, 2, 3, 4 and so on. Weight is the body weight of that subject. Dose is the dose of theophylline, which is a drug that has been given in milligrams per kg body weight, and time is the time that has elapsed, and concentration is the concentration of theophylline in the blood. So as you can see, over time points, data has been collected for subject 1, 2, 3, 4, and concentration has been noted down of theophylline. And basically we want to see how does the concentration change over time. That is our basic research question. So how does the concentration change over time for this drug in patients? Now this dataset is not very complex. In reality, there may be many more variables which might influence the concentration of theophylline or the rate of decrease of theophylline concentration in the blood, but we are going to limit ourselves to few simple variables to make our models and interpretability easy. So first of all, I will be categorizing our data into certain categories. So I will be cutting our dose data into 3 to 4, 4 to 5 and 5 to 6 milligram per kg categories. Similarly for weight, those between 50 to 60 kilograms, those between 60 to 70 and so on. So let's do that. If you were, in case you were wondering, the cut function does this, and this is the syntax to do that. Pretty easy. And let us first see a few descriptive statistics, summary statistics of our data. So we can see the median weight of the patient is 71 kilograms. The median dose of theophylline that was given was 4.5 milligram per kilogram. This is not needed interpretation, and the median concentration was 6.3 over the time that was time the concentration was measured, and these are our categories. So we can see many of the patients were given between 4 to 5 mg per kg, and most of the participants were between 70 to 80 kilograms body weight. So let us now visualize our data. So the ggScatter function from the ggpubr package helps us to analyze, helps us to plot the data, and the first plot is a very simple plot without any grouping variable as such, and we can see prima facie for all the subjects there is a fairly linear downtrend, negative trend. So we can see, okay, so there's a fairly linear decline in theophylline concentrations over time, and that is good. Otherwise we would have to make provisions for non-linear models, and in the coming few tutorials I will show how to model non-linear data using splines, using generalized additive models and so on. But this data set pretty good, and this is why it's very important to visualize our data first before jumping or diving headfirst into any sort of modeling. Very important to visualize data. Now let's see the effect of dose on concentration. And as expected, those with higher doses, 5 to 6 milligrams per kilograms, had obviously started out with higher concentrations, but you can see the slope, that is the rate of decline, is fairly similar. So, we can comment that, all right, it seems that the whatever dose you give to the participant, the rate of decline is still the same. All right, pretty useful insight into our data. And the last graph is grouped over patient body weight. So this is also fairly intuitive. Patients with higher body weights had lower concentrations, and patients with lower body weight had higher concentrations of theophylline in their blood. Pretty intuitive, because those with lower body weights, obviously they will have a lot of the drug in their bloodstream due to various factors, lipophilicity, first pass metabolism, many such factors influence the concentration. And in those with higher body weights, the inverse of that. So now that we have these important insights into our data, let us now begin to model. Now, I have already discussed what we want to see. We want to see the effect of time on concentration, right? How does the concentration of theophylline change over time? But we also want to see the effect of dose given and the body weight of the participants on the concentration, right? So if we just wanted to see the effect of time on concentration, we could have just used a repeated measures ANOVA, right? There are less assumptions, statistical assumptions that need to be met for RM ANOVA than mixed effects models, but it lacks the flexibility of adjusting for variables and other such things. An important one of them includes nested mixed effects or random effects, which we will cover shortly. Now let us skip the assumptions for now. Let's come back to this later. But the first model that we will try to fit is an unadjusted mixed effects model. So now we're beginning to throw multiple terms together, unadjusted mixed effects models, but I promise it's really simple, conceptually really simple. Unadjusted, we are not adjusting for any extraneous factor, weight, dose, gender, what have you. And mixed effects, fixed effects plus a random effect for clustered data. So this is the syntax, this is the function, LMER is the function. If you remember, for simple linear regression, it's just LM. This is the syntax for linear mixed effects regression, LMER. And conc is our concentration of theophylline. Time is of course our time elapsed, and this is our syntax for including random effects. Now what does this mean? So basically this means that each subject is considered as a random intercept. Okay, intercept, what intercept? Intercept. See here, in any type of regression you will have an intercept. That is the value of y when x is 0. That is an intercept. So each subject is considered as a random intercept, and that basically in intuitive terms means that each subject has, the data for each subject has certain characteristics which make it correlated to one another for each subject. Subject 1 correlated, subject 2 correlated, just like the forest example that we discussed in the beginning. So this is the syntax, very simple. If you have longitudinal data, or clustered data, please use this syntax. And the rest of the syntax is the same. Summary will get us this summary write-up or a summary analysis. The report function will, from the report library, will give us a very nice statistical report, very useful. And this TBL regression will give us a table from the GT summary package. So let us see what this model has done. Now we see that time is our fixed effect. In any simple linear regression, not mixed effects regression, any simple linear regression, all your predictor variables or your independent variables, all of them are fixed effects. So this is our fixed effect time. We have a negative beta coefficient, negative 0.45, and we have a highly significant p-value. So negative 0.45, and how do we interpret this? So for each second increase in time, because time is in seconds or minutes, so for each minute increase in time, pardon me, oh, I was wrong twice, it's hour. So for each hour increase in time, the concentration of theophylline decreases by 0.45 milligrams per liter. Let me reiterate. For each hour increase in time, or for each unit increase in time, the concentration of theophylline, the dependent variable, decreases by 0.45 milligrams per liter, or 0.45 units, which is a significant result. And the R squared, where is the R squared, is 0.96, and this is really good. The model fit is extremely good, suspiciously too good. 0.96, 96%. It explains the variance of concentration. So at this point we could just call it quits. Why adjust for other factors? We already have a certain variable, time in this case, which explains 96% of the concentration variance. Pretty good. But let us trot on and let us explore if the dose or body weight changes the model. Now, before we model further, I would like to draw your attention to these two graphs. Looking at these two graphs, do you think the dose or the body weight would influence the concentration? What do you think? I encourage you all to pause this video and think about it. Alright? The answer is no. I don't think that the dose or body weight will influence the concentration, because okay, there are effects, there are differences in the straight lines, there are gaps in the straight lines in layman's terms, but the slope, look at the slope, look at the rate, the slope, the change in concentration, it's almost the same. Okay, these are converging, probably not the same, similar. Same with the body weight, the slopes are pretty similar. So I am not expecting significant results for when we include the dose and the weight in our model. I'm not expecting significant results. Like we said, time explains 96% of the model variance. So going forward, I don't believe that will influence the model further. Now, this is just a short explanation for a random intercept and what it does. Basically, what I've talked about, nothing new. You can pause the video and read what the random intercept does if you wish. Now we will come to this nested random effect in a bit. Alright, so now is the moment of truth. So in our exploratory data analysis, we saw that alright, weight and dose does not seem to have an effect. So is that really the case? Like a simple linear regression model, just add these two terms as fixed effects, and now let's see. Let's run this, and now let's see. What do we have here? Weight, no difference. Perfect. Dose, all right. 3 to 4 and 4 to 5 does not seem to have a big difference, but apparently this is 0.04, almost on the verge of borderline significance. 0.04, a p-value 0.04, not really too much significant, borderline I would say. Look at the confidence intervals, 0.35. So realistically speaking, even though this is a statistically significant result, it might not be very clinically significant. So now that we are seeing this, let us go back to the graph, and this is 3 to 4 and this is 5 to 6. Okay, we can see some convergence of the blue line and the orange line. So all right, I mean, might be the slopes might be different, not too much. It's just the confidence interval. See the confidence interval, it's not too much. So I won't read too much into this significant p-value, and this is just the same. This is the same thing, the same table in a very non-user friendly format. All right, now what is this? This is known as a nested random effect. For example, if we have reason to believe that each individual, the dose of theophylline given to each individual makes a difference in the concentration. For example, if each individual processes different types of doses differently, it might make a difference. For example, if you give individual A dose 3 to 4, 4 to 5, 5 to 6, and if you have reason to think that he will process each dose differently, for example, you have reason to think he or she will process dose between 5 to 6 differently, that is, the concentration will reduce drastically, the rate of concentration decrease will reduce drastically, and say between 3 to 4 the slope will not be too much, that is, the rate will not be too much of theophylline reduction, concentration reduction in the blood, then because you think that each individual metabolizes or processes each dose differently, then you could potentially use something like this. So you include dose as a random effect and you nest each subject in that dose. This is called a nested random effects model. Now we are getting too much, we are making the model too complex. Important thing to note, if you do not have much data per subject for each of these variables or each of the fixed effects as well, I would encourage not to make a very complex hierarchical model. So here you can see how the data is hierarchical, right? It is now apparent how hierarchy, dose, subject, then fixed effects, this hierarchy is now apparent. So I would not use this model because it is too complex for the question that we have. I might have reason to think that each subject processes different doses differently, might be different liver physiology, might be different pharmacokinetics, might be different pharmacodynamics. I might have some reason to think, but I will not use this model, and we get a model here. Basically, this model means just stop. Your model is becoming too complex for your data. Either increase the number of data points per dose and per subject time, weight for each subject, or make a simpler model. So that's what we did. Make a simple model. Just include each subject as a random input set. Don't make a nested mixed effects model. This was just to show how you would potentially approach such a question. And this is just a write up about the same. Now, just a little bonus, the visreg package, visualization of a regression, visreg, gives us good functionality to visualize the regression. Now this is not a regression, this is just a simple linear regression. This does not account for mixed effects. So to account for mixed effects, the visreg will account for your mixed effects. Just plug in the object that you have used to store your mixed effects models and run this code, and you get a nice regression model. So the function of time basically is the concentration, and you can see that the blue and the red line are converging. That's what we saw, but there's no effect of patient body weight. All these lines are pretty straight to me, and this is just to show the highly complex model, this one, the nested model. All right, and last but not least is estimated marginal means, or EM means, also known as least square means, also known as adjusted means. So you basically adjust for factors such as time or weight or dose that you have in the model, and you get basically the mean concentration for a certain time point for these body weights, similarly for different doses, and you also get contrasts that are basically the differences in adjusted means, difference of adjusted means, or adjusted mean difference. That is it. And you can see a significant, well, not a significant, but almost tending to significant p-value between 5 to 6 and 3 to 4. That's what we saw in this graph as well, blue and red. So this was all about mixed effects models, linear mixed effects modeling, and I hope this was an interesting video on how to model. Basically, this gives you flexibility and freedom. I almost left out the assumption checks. These checks are very important, and the first one is linearity of predictors, very easily plotted using a graph. Second is independence between subjects, should not repeat two subjects. Ideally, this assumption is moot because you include each subject as a random intercept. The independence of residuals, there should not be any pattern to your data. I don't see any pattern, just plot the time and residuals of your model fit. Homoscedasticity, there is no overt change in variance. Here we can see maybe after 7 to 10, between 7 to 10, I think there might be a change in variance, but it is not too drastic. And last but not least, normality of residuals. You can plot a QQ plot, that is a quantile plot, or a histogram, and for the most part this looks normally distributed, might be a little positively skewed, but I would say it's fine for the model. I won't read too much into it. So this was all about mixed effects regression. Please let me know down in the comments if you have any questions. Thanks for watching.